In this recording, we're going to define something called the area accumulation function. And the area accumulation function is a very important function inside of integral calculus. To get started, I want to let the function a sub f of x be defined as the definite integral from a to x of f of t dt. Now that's a strange way of defining a function if you think about it, and so we need to make sense out of this definition. And I want to draw a picture by hand, but then we're going to also start looking at pictures drawn by Mathematica. So let's see if I can draw a halfway decent picture by hand. So here's an xy, well actually I want this to be a ty coordinate plane, and I want some kind of a function. So let me actually have a function that does something like that. And this is the function y is equal to f of t. And I want to define an a value. And the a value is the start of my integral. Now, what I want to do is I want to think about letting x vary. Now, x can be, if x is bigger than a, then x is going to be somewhere out here. And what I'm going to do is I'm going to draw several little kinds of candidates for that particular x. So we've got an x1 and an x2 and an x3 and an x4 and an x5. And essentially, AF of x1 would be that little chunk of area. Now, when I get out to AX2, I'm going to have all of this area minus that area. When I get out to X3, it's going to be this area minus all of this area. And when I get out to X4, I'd be looking at positive this area minus this whole area, and then positive this area. And so on and so forth. So if x is bigger than a, then the value of the function a of x is going to be, well, it's of course going to be this integral, but it's going to be the area that is above the x-axis. And my handwriting is letting me down. So it's the area above the x-axis minus the area below the x-axis, and between t equals a and t equals x, because formally this line is formally that line is t is equal to a. And if I have an x value like this one here, this would be t is equal to x. Now, of course, we could also have values for x that are less than a. So I also want to look at that particular picture. Let's see, this color I think will do. So if x is less than a, then we are going to be integrating in the backwards direction. A of x is still going to be a to x of f of t dt, but in this case, the bottom endpoint is the big one, so we are integrating backwards. And because we're integrating backwards, when x is smaller than a, the value of the area accumulation function is going to be the area below the x-axis subtract off the area above the x-axis, and again, this is between t is equal to a and t is equal to x. And it's just that we're going backwards. To make this clearer, I want to now look at some pictures that are drawn in Mathematica. So let's now go to my Mathematica window. This notebook will be put onto Blackboard so you can play with it as you want to, and so it will be made available to you. So the very first thing is I want to say that in a typical situation, I'm going to let my function be x plus cosine of 3x minus 0.45. And we're going to look at, of course, the area accumulation function given by that particular integer. This particular cell gives us a basic idea of what the function is going to do, and this is also illustrating something important. Whenever you see this message pop up in Mathematica, always say yes. And so this is what my function looks like. Now, because my integral, and this is my integral, because my integral is starting at 0, I want to be thinking in terms of drawing out the area as x is going to be going this way. Now, I've written a function called the area accumulation function, and we can figure out how to use it by evaluating this cell. And I encourage you to stop the video and read this. What this says is that to use the area accumulation function, I have to give it the function, I have to tell it that t is the variable, and then I have to give it the starting value for the function and a left and right value for the plot. So we're going to use the area accumulation function setting a equal to 0, and I'm just going to make the plot go from a, which is 0, to 2. And when I do, I get this lovely little picture. Now, the nice thing is when there's this plus sign, you can click on it and you get a slider bar, but inside this particular box will be the value of x. I also want you to notice that x and a are labeled down here on the graph. And as I pull x away, you can see how the shaded area accumulates. And the other thing that you can see is that I'm shading the positive area blue and the negative area red. Now, if I go back to the beginning of this particular picture, I want to notice that this particular part of the cell here tells you what the actual shaded area is. And this is the shaded signed area. And you should notice that as x is increasing, this number first of all goes up, and then it goes down. And it starts to go down right at the place where f of x becomes negative. And so I encourage you to play with this notebook on your own at some point. Well, I also want to make sure that we can look at backwards integrating. So here what I want to do is keep the same function, but I want to look at some negative x values as well. So here is a range of values going all the way down to -2 and all the way up to +2. I'm going to go ahead and continue to let the start of the interval for my area accumulation function be equal to 0. And so this is what the area accumulation function would look like this time. Again, we're starting at a is equal to 0, and so there is no area at that particular point. But as I increase x, you'll notice, oh, that's the same picture that we had before. If I come back and start this guy at 0 again, and I pull x going the other way, you will notice that as expected, because we are integrating in the backwards direction, when we have area above the x-axis and below the curve, that's being subtracted off the definite integral, and when the area is below the x-axis, it is getting added as a positive area because we are integrating from right to left instead of in the normal order from left to right. Again, play around with this on your own. Download the notebook and play around with it. The final thing that I want to note is that there's absolutely nothing special about starting the area accumulation function at a is equal to 0. This particular area accumulation function has the bottom endpoint being -1. Well, if I want to look at the picture there, this is what happens. And the only real difference is that my starting line is over here at -1. But if I pull x towards the right, the integral behaves in the normal fashion. The area that is below the x-axis is colored red because it's being treated as negative. The area that is above the x-axis is colored blue because it is being considered positive area. And where I'm currently stopped, the accumulated area is negative, and that's because this chunk of area is bigger than this chunk of area, and these two areas are just about canceling each other out. But this is the biggest chunk of area, and it's still dominating the size of this. If I go back to the starting value of 0 and pull x the other way, if I go back to x's starting value, oh, the starting value is not 0 anymore. Let me go back to the starting value. The starting value is -1. Sorry about that. So if I go back to the starting value and I pull x in the negative direction, you'll notice that all of this area is currently positive because we are integrating in the wrong order. We are going from right to left, and hence the width of the area is negative, and so the height being negative and the width being negative yields negative times negative is equal to positive, a positive area. Finally, as one more example, we can look at this area accumulation function. All I've done here is I have changed the bottom endpoint from from 0 or -1 to a +1. This particular input cell lets me, let's I correct that typo, this will let me draw out that particular area. And again, when I have x move towards the right, the integral is being traced out in the correct way, so area that is below the x-axis is colored red, area that is above the x-axis is colored blue because it's positive. Obviously, if I stop here, the blue area is a lot bigger than that red area, and my accumulated area is positive. If I go back to my starting value of 1, and I pull x to the left, we will notice that the integral is going in the wrong direction, and the area underneath the x-axis is now considered positive. The area above the x-axis is considered negative, and the reason why is, again, that the width is negative, and negative times negative is a positive, so that's why this area over here is positive. Negative times positive is negative, and that's why this area here in the middle is negative. Again, if I come back and look at this, when I'm in through here and this chunk of red is bigger than that chunk of blue, this particular integral is indeed negative as expected. So that gives you a basic introduction to how the area accumulation functions actually behave. We will look at this in much more detail in this week's lab.